Hello everyone! Today we will have a new lesson about number system conversion, binary, decimal, octal, and hexadecimal. As we know, the number system is a form of expressing the numbers. In number system conversion, we will study to convert a number of one base to a number of another base. There are a variety of number systems such as binary numbers, decimal numbers, hexadecimal numbers, octal numbers, which can be exercised. As you know, decimal, binary, octal, and hexadecimal number systems are positional value number systems. To convert binary, octal, and hexadecimal to decimal number, we just need to add the product of each digit with its positional value. Here we are going to learn other conversion among these number systems. Binary is the simplest kind of number system that uses only two digits of 0 and 1, such as value of base 2. Since digital electronics have only these two states, either 0 or 1, so binary number is most preferred in modern computer engineer, networking, and communication specialists and other professionals. Whereas decimal number is most familiar number system to the general public. It is base 10, which has only 10 symbols: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let us see the number system conversion table. So this is the number system conversion table that has binary numbers, octal numbers, decimal numbers, hexadecimal numbers. So what are the number system conversion methods? Number system conversions deal with the operations to change the base of the numbers. For example, to change a decimal number with base 10 to binary number with base 2. We can also perform the arithmetic operations like the addition, subtraction, multiplication on the number system. Here, we will learn the methods to convert the number of one base to the number of another base, starting with the decimal number system. The representation of number system base conversion in general form for any base number is the following. In the above expression, d n minus 1 and d n minus 2, then d1, d0, d negative 2, and so on, or d negative m, represents the fractional part. d n minus 1 is the most significant bit, or MSB. d minus m is the least significant bit, or LSB. Now, let us learn conversion from one base to another. So, decimal to other bases. Converting a decimal number to other base numbers is easy. We have to divide the decimal number by the converted value of the new base. So, let us review or recall the base and its representation. Base 2 for the binary, base 8 for the octal, base 10 to the decimal, and base 16 for the hexadecimal. Let us talk about decimal to binary. Decimal numbers can be converted to binary by repeated division of the number by 2 while recording the remainder. Let's take an example to see how this happens. So for the example, the remainders are to be read from bottom to top to obtain the binary equivalent. So as you can see, For example, 43 divided by 2, then 21. So 21 times 2 is 42, then the remainder is 1. Then 21 divided by 2 is equal to 10. 10 times 2 is equals to 20, and then the remainder is 1. Then 10 divided by 2 is 5. 5 times 2 is equals to 10, so there is 0 remainder. Next, 5 divided by 2 is 2. 2 times 2 is equals to 4. Then the remainder is 1. Then 2 divided by 2 is equal to 1. 1 times 2 is equal to 2, so there is 0 remainder. And then the last number is 1. So the answer would be from 43 in decimal, the corresponding binary is 101011. Another example for decimal to binary. So the given number is 10.25 in decimal. So take a look at the screen. So take note, keep multiplying the fractional part with 2 until decimal part 0.00 is obtained. So for the given example, the fractional part is 0.25 times 2 is equal to 0.50. Then 0.50 times 2 is equal to 1.00. So the answer from the 10.25 in decimal is equal to 1010.01 in binary. Suppose if we have to convert decimal to binary, then divide the decimal number by 2. For example, convert 25 decimal to binary number. So for the solution, let us create a table based on this question. So here is the table. For the solution is 25 divided by 2 is equal to 12. Then 12 times 2 is equal to 24, so the remainder will be 1. Next, as an output, 12 divided by 2 is equal to 6. 6 times 2 is exactly 12, so there is 0 remainder. Next, for the output, 6 divided by 2 is equal to 3. 3 times 2 is equal to 6, and there is 0 remainder. Next is the output 3. 3 divided by 2 is equal to 1. 1 times 2 is equal to 2, so the remainder will be 1. Next output, 1 divided by 2 is equal to 0. 0 times 2 is 0, so the remainder will be 1. So for the answer of 25 in decimal is equivalent to 11001 in binary. Let's proceed to decimal to octal. Decimal numbers can be converted to octal by repeated division of the number by 8 while recording the remainder. Let's take an example to see how this happens. So for the example, the given is 473 in decimal, and we are going to convert into octal. So the solution will be 473 divided by 8. So the output will be 59, and then followed by 59 divided by 8. So there will be a remainder of 1. Next, 7 divided by 8. and there will be a remainder of 7 until it comes to 0. So for the remainder of 473 in decimal will be 1, 3, and 7. Take note, reading the remainders from bottom to top. So the answer for the 473 in decimal is equivalent to 731 in octal. To convert the decimal to octal number, we have to divide the given original number by 8 such that base 10 changes to base 8. Let us understand with the help of an example. So the next example will be convert 128 in decimal to octal number. So for the solution, let us represent the conversion in tabular form. So for the solution, 128 divided by 8, then the output would be 16. And then the remainder would be 0. Next, 16 divided by 8 is equal to 2. 2 times 8 is equal to 16. So there will be still 0 remainder. Next, for the output is 2 divided by 8 is equal to 0. 0 times 2 is equal to 0. So there will be a remainder of 2. So therefore, the equivalent octal number is equal to 200. And for additional example from decimal to octal, 10.25. So the fractional part here is 0.25 times 8, which is equals to 2.00. Note, keep multiplying the fractional part with an 8 until decimal part 0.00 is obtained. So here for the example, 0.25 in decimal is equal to 0.2 in octal. So the answer from 10.25 in decimal is equal to 12.2 in octal. Let's talk about this decimal to hexadecimal. Decimal numbers can be converted to octal by repeated division of the number by 16 while recording the remainder. Let's take an example to see how this happens. So for the example, the given is 423 in decimal, and the solution will be 423 divided by 16. Then we will get the answer 26, and the remainder is 7. Then 26 divided by 16, then will be the answer is 1, and then the remainder is A or 10. Then 1 divided by 16 is equal to 0. Then 0 times 16 or 0 times 1 is equal to 0. Then the remainder would be 1. So reading the remainders from bottom to top, we will get 423 decimal is equivalent to 1A7 in hexadecimal. Again, in decimal to hex conversion, we have to divide the given decimal number by 16. So for the example, convert 128 decimal to hexadecimal. And the solution, as per the method, we can create a table. So here, 128 divided by 16, the output will be 8, and there is 0 remainder. The next, 8 divided by 16 is equal to 0, and the remainder would be 8. Therefore, the equivalent hexadecimal number is 80. Here, MSB stands for a most significant bit, while LSB stands for a least significant bit. But how are other base systems to decimal conversion. First, let's try binary to decimal. In this conversion binary number to a decimal number, we use multiplication method in such a way that if a number with base n has to be converted into a number with base 10, then each digit of the given number is multiplied from MSB to LSB with reducing the power of the base. Let us understand this conversion with the help of an example. So the given will be 1101 binary convert into a decimal number. For the solution, given a binary number 1101, now multiplying each digit from MSB to LSB with reducing the power of the base number 2. So for the solution, 1 times 2 to the third power plus 1 times 2 to the second power plus 0 times 2 to the first power plus 1 times 2 to the 0 power. So the answer will be 8 plus 4 plus 0 plus 1, then add is equal to 13. So therefore, 1101 binary is equivalent to 13 in decimal. Another example, the given number is 1010.01 in binary. So for the solution, 1 times 2 to the third power plus 0 times 2 to the second power plus 1 times 2 to the first power plus 0 times 2 to the 0 power plus 0 times 2 to negative 1 since we're the decimal point plus 1 times 2 to the negative 2 power. So do the operation, it would be 8 plus 0 plus 2 plus 0 plus 0 plus 0.25 for the decimal part, for the fractional part, is equal to 10.25. So 1010.01 binary number is equal to 10.25 in decimal number. Let's proceed to the octal to decimal. To convert octal to decimal, we multiply the digits of octal number with increasing power of the base number 8, starting from MSB to LSB, and then add them all together. For the example, convert 22 octal number to decimal number. Solution, as given 22 octal number, 2 times 8 to the first power plus 2 times 8 to the 0 power. It would be 16 plus 2 is equals to 18. Therefore, 22 octal number is equal to 18 decimal number. Another example, the given is 12.2 octal number. Then the solution is 1 times 8 to the first power plus 2 times 8 to the 0 power plus 2 times 8 to the negative 1 power as a fractional part. Then do the operation, it would be 8 plus 2 plus 0.25 is equal to 10.25. So the corresponding decimal number of 12.2 octal is 10.25. How about hexadecimal to decimal? For example, convert 121 hexadecimal number to decimal number. And the solution would be 1 times 16 to the second power plus 2 times 16 to the first power plus 1 times 16 to the 0 power. Then followed by 16 times 16 plus 2 times 16 plus 1 times 1 is equals to 289. Therefore, 121 in hexadecimal number is equals to 289 in decimal number. Next is hexadecimal to decimal. To convert a binary number to octal number, these steps are followed. So this is for the binary to octal and vice versa. Starting from the least significant bit, make groups of 3 bits. If there are 1 or 2 bits less in making the groups, zeros can be added after the most significant bit. Convert each group into its equivalent octal number. Let's take an example to understand this. So, the given is 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1. So, as the step, make groups of 3 bits. So, divide into 3 bits, it would be 0, 1, 0, then 1, 1, 0, then 0, 1, 0, and 1, 0, 1. 1, 0, 1 is equivalent to 5. 0, 1, 0 is equivalent to 2. 1, 1, 0 is equivalent to 6. And 0, 1, 0 is equivalent to 2. So the corresponding octal value for 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1 binary number is 2625 in octal number. To convert an octal number to binary, each octal digit is converted to its 3-bit binary equivalent according to this table. So, for the binary equivalent of 0 is 0, 0, 0. Then for 1 is 0, 0, 1. For number 2 is 0, 1, 0. Number 3, 0, 1, 1. 4 is 1, 0, 0. 5, 4, 1, 0, 1. And 6, 1, 1, 0. And for 7 is 1, 1, 1. So, for the equivalent binary number of 54673 octal is 1011011011111 in binary. How about octal to binary shortcut method? To convert octal to binary number, we can simply use the table, just like having a table for hexadecimal and its equivalent binary. In the same way, we have a table for octal and its equivalent binary number. So for the octal in binary, example, convert 214 octal number into a binary number. And the solution from the table, we know 2 is equivalent for 0, 1, 0, 1 is equivalent to 0, 0, 1, and 4 is equivalent to 1, 0, 0. Therefore, the given octal number 214 is equivalent to 0, 1, 0, 0, 0, 1, 1, 0, 0 in binary number. Let's proceed to the binary to hexadecimal. To convert a binary number to hexadecimal number, these steps are followed. Starting from the least significant bit, make groups of 4 bits. If there are 1 or 2 bits less in making the groups, zeros can be added after the most significant bit. Then convert each group into its equivalent octal number. So let's take an example to understand this. The given is 10110110101101. As the step said, divide or group it into 4 bits. So it will be 1101, then next is 1011, and the next is 0101. So the corresponding value for 0101 is 5, then 1011 is B, and 1101 is D. So therefore, the binary number 10110110101 is equivalent to DB5 of hexadecimal number. Next, discuss hexadecimal to binary shortcut method. So you can easily solve the problems based on hexadecimal and binary conversions with the help of this table. Let us take an example. So for example, binary equivalent and then hexadecimal from 0 to 9 and A to F. For example, convert 89 hexadecimal number into a binary number. For the solution, from the table, we can get the binary value of 89 hexadecimal base numbers. So 8 is equivalent to 1000 and 9 is equivalent to 1001. Therefore, 89 as a hexadecimal number is equivalent to 10001001 binary number. To convert from hexadecimal to binary, write the 4-bit binary equivalent of hexadecimal. So another example, 3A as a hexadecimal number is equivalent to 00111010 in binary number. Another example, to convert from binary to hexadecimal, group the bits in groups of 4 and write the hex for the 4-bit binary. Add zeros to adjust the groups. So the given is 1111011011. So add 0. It would be 0011101111 in binary number is equivalent of 3dB in hexadecimal number. So that's all for the discussion about the number system conversions such as binary, decimal, octal, and hexadecimal. Thank you for watching and have a nice day.